Okay, this is going to be our review session for exam 4, which is going to cover chapter 7 only. I'll ask names of halides. Chapter 7 is on alkyl halide. So I'll give you a compound like this. C, 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 and then you have H, Br, Br, iodine, and rest are hydrogen, but I can still write down the hydrogen, CH3, obviously. That's that. So if you want to number this, I have two substitution groups here, so let's number it. 1 here, 2 here, and this 3. This is propane, is the longest chain, having 3 carbon. So you can write it down as 1, 1 dibromo. Dibromo 2 iodo. Now here we go by alphabetic ordering. B, bromo comes first before iodo. 1, 1 dibromo 2 iodo, and then you can write down the name of the rest of the molecule. There are 3 carbons, it's a propane. So one such naming would be on the test, on 1 or 2 questions would be on the test on naming of alkyl halide. Next type of question would be on reaction rate. Some reactions would happen faster than the others, but in many cases we can predict in which case reaction would be faster. Just by looking at the leaving group, the group which is leaving, if can leave quite quickly, that means that reaction would happen faster. So let me give you 2 examples. That's Cl. And say I'm reacting it with sodium hydroxide. Sodium hydroxide is going to give OH minus, and OH minus will be looking for this carbon. So this, keep in mind, this is carbon, that the positive center, because Cl is attracting electron away from carbon, so that makes it delta plus. This is delta minus. So that's going to invite OH to go over there, OH with electron pairs. So OH is going to be nucleophile. It loves the positive center, and this carbon is going to be electrophile. It's going to invite this electron from OH. So in other words, OH minus will be attracted to that, and your final product is going to be this. These are carbons. Now I can write down another reaction, and then you can examine which reaction will be faster. In this case, I would have I, again, OH minus, so it's going to be OH. Now if I give you these 2 reactions and ask you which one would be faster, your answer would be this. The second one is going to be faster because of iodine. These are substitution reaction, OH is taking the place of halogen. So both are substitution reactions. And this is 1 degree carbon. Keep this in mind, this is 1 degree, because this halide, this carbon is bonded to only one other carbon, so this is 1 degree. So in 1 degree halide, this substitution would be called SN2 substitution reaction. But which one will be faster? This one will be faster, because iodine is a much better leaving group. As soon as it sees OH minus coming, it's going to leave and make the room for OH minus. Otherwise, there will be too many bonds on this carbon, because that carbon must have 4 bonds. Don't forget that there are 2 hydrogens already there on that carbon. So, which leaving group, these are the best leaving groups among the halogens. Iodine, and iodide ion, much better leaving group than Br minus. Then Br minus is better leaving group than Cl minus, than F minus. So F minus is the worst one as living group. So your answer to this question would be, if this kind of reactions are given, substitution reaction would be SN2 type because of this 1 degree halide, which only allows SN2, not SN1. Just to remind you, in SN1 it goes through carbocation. That means halogen has to get separate first, then there will be carbocation, and then the second step of reaction will happen. That would have been SN1. But since this is a 1 degree halide, so it's going to be SN2, and this is going to be faster because of the leaving group. Iodide is a much better leaving group than chloride. So from this example, we explained which one will be faster and what type of reaction, substitution reaction you'd expect. So we explained that SN2 or SN1, and also we mentioned about what kind of halide we dealt with. That was 1 degree halide. Now let me show you what could be 2 degree halide. Say I have Cl bonded to this compound. Now this would have been still 1 degree because there's one other carbon. If there's another carbon here, that would have been 2 degree halide. That's 2 degree. Because this carbon is bonded to 2 other carbons. Now if I have 3 degree, then it will look like this. I'm writing on C and say another C here. This is 3 degree because this is the carbon which is holding Cl. Is bonded to 3 other carbon. This carbon, this carbon, this carbon. So that's 3 degree. In this kind of cases, halogen gets separated. So SN2 reaction doesn't happen. So halogen gets separated and you get a carbocation here, and that would allow SN1 type of reaction when there is substitution reaction. Now, quite often we deal with a steric hindrance. If I have a big group, that's going to slow down a reaction. So let me write down one structure of halide, and you'd have an idea what I mean by slowing down of reaction. So CCl, and then you have a C here. Then I have 3 ethyl groups. I left out hydrogens, and these are carbons. Keep that in mind. These are ethyl groups. Now, quite often students make a mistake in determining what kind of halide is this. This is the carbon you'd be looking at, because that's holding Cl. And that's attached to only one other carbon, so it's 1 degree. It's not 3 degree. So this is the 1 degree halide. But what is remarkable in this case is there's a big groups here. This is ethyl groups. Let's write down more explicitly. CC, CC, and so this is going to be CH2, CH3. So this is going to be CH3, CH2. CH2, CH3. So you're talking about big groups here, here, here. Now say I'm reacting it with Ki, potassium iodide. So iodide is going to come over here, it will get bonded to carbon and then this carbon, and then this Cl has to get out. So basically this is what I would end up with. C, I is going to take the place, then these groups are going to remain same as it is. Well, the question is, which reaction will be faster? Let's draw another one. CCl, Ki, where I is minus and K is plus. So this is going to give CCI. Obviously, this is going to be faster. Why? We call it a steric hindrance. This has 3 big groups around this carbon, and that's going to slow down the attachment of iodine to this carbon. So that's going to make this reaction go slowly. On the other hand, the steric hindrance is much lower for this carbon. So this can be readily replaced by iodine, so it will be faster. So in rate of reaction, you should pay attention to not just the leaving group, also what other groups are bonded or steric hindrance that you need to look at too. Now, sometimes I give a compound like this, CCl, and then ethyl, and another one methyl group here. So, and say I'm adding water there. Now, water addition happens at HOH. OH is the negative part. That's going to replace the Cl. So your final product is going to have OH in there. So let's write down here, not to make it confusing, CH3. And these are CH2CH3. Now, question is, if I get a reaction like this, where this is going to be replaced by OH, and also I would have a second product, which would be given by elimination. So let's write down that, C, and then OH. So this is one of the products. The other product is C, and then you have a double bond here. Okay. And then you'd have OH. Sorry, there's no OH here. This is the other product. Let me make sure that I haven't left out anything. So what had happened is, this is a 3-degree carbon, 3-degree halide. In 3-degree halide is the halogen that comes out first. So it's not going to be SN2 or E2 type of reaction. So when this comes out, so keep that in mind, in 1 degree and 2 degree it doesn't happen that fast. But for 3 degree it happens, and then you get a carbocation like this. This is carbocation. It's an intermediate carbocation. So now it can either do substitution reaction. If OH minus gets bonded, it's substitution, then it becomes SN1. Why SN1? It goes through carbocation. Whenever it happens, substitution happens through carbocation, that means first living group leaves, then the next group comes in, and it's called SN1, substitution unimolecular. This molecule is the dominant one in this reaction. You can also have elimination from carbocation. So substitution or elimination. Both can happen at the same time. In case of elimination reaction, you're going to get E1, not E2. Whenever elimination happens after formation of carbocation is E1. So there will be a question like this. Now, I can also give you a mechanism, and I need to find out what kind of elimination reaction you got. Is that E1 or E2? Let me show you one such mechanism. So this is hydrogen. I have 3-carbon compound, 3-carbon group here, iodine, and then phenyl group here, and H. Say I'm adding a base, OH minus. This is a good living group, so OH minus has to pick this hydrogen, so hydrogen get bonded. And why? What's the motivation for this? Because this iodine would like to leave. As soon as this forms the double bond, and iodine leaves. So basically you make a double bond here, iodine goes, so you have an unsaturation form. So it's an elimination reaction. But what kind of elimination? Both these steps are happening happening at the same time. So it's called E2. Elimination, it doesn't go through carbocation. Why it doesn't go through carbocation? Look at this carbon. This is 2-degree carbon. This is one carbon is bonded, the second one. So for 1 degree, 2 degree, if it's a substitution, it will be SN2. If it's elimination, it's E2. For 3 degree, if it's substitution, it's SN1. And elimination is going to be E1. So keep that in mind. Then several other reactions we need to know. If I have an alcohol now what kind of alcohol is this again? Examine this carbon. It's bonded to one other carbon. So this is 1 degree. 1 degree alcohol. If I want to get halide, if it's 1 degree, in order to get halide, you need to use thionyl chloride. Yes, that's going to change it to halide. This is going to work for 1 degree as well as 2 degree. But not for 3 degree. If I have 3 degree, let me show you the 3 degree. This is OH, and I have, say, so this is the carbon that bonded to 3 other carbons, 1, 2, and 3. And if this is what I have, it's not thionyl chloride you're going to use, just simply HCl. So this is for 3 degree alcohol. Having HCl, you get and keep in mind this is carbon. Carbon, 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 carbon. I left out hydrogen. So make sure you stick in hydrogen so that each carbon gets 4 bonds. So this is going to be the product. So you should know how do I convert alcohol to halide. So just keep in mind for 3 degrees it's just purely an acid. You're going to add HCl, HBr, HI. For 1 degree, thionyl chloride for chloride, PBr3 for Br, and Pi3 for iodine. Next type of reaction, which is very important, is called Grignard reagent. So there will be a question on Grignard reaction and Grignard reagent. It's not just this exam. In future exams also there could be a question on Grignard reagents. Now I'll give you a simple example of this reaction. Okay, so this is a halide, and I want to change it to a Grignard compound so that I can do the next step of calculation. For that, you need to use magnesium and ether. What it does, it changes the bonding pattern in here. It's no longer CBr bond. That's what you're going to get once you have magnesium and ether added there. So then this becomes minus, and this becomes ionic bond, Mg, and then Br. And this is the key thing in Grignard reaction. This is highly reactive. This negatively charged carbon, it can combine with any hydrogen or any other positive element. So if I use H2O, hydrogen is going to stick here. If I'm going to use D2O, scientists in earlier years, that's what they tried. It's a heavy water, D2O. Then you end up with this. So that scientists know where that hydrogen goes. So D2O is really heavier hydrogen. So that's how scientists know the mechanism involving Grignard reaction. So you need to know about what reagents make Grignard, what is Grignard reagent, and how do I make it from alkyl halide. And this is alkyl halide, then you can using magnesium and ether, that gives you alkyl magnesium halide. That's Grignard reagent. Now often we show alkyl groups with R rather than specifically writing down methyl, ethyl, or propyl. For example, if I'm writing down R3CX, what I'm saying is here, carbon has 3 alkyl groups, and there is a halogen is normally shown with X, or a leaving group shown with X. So this makes that, this alkyl could be methyl, ethyl, propyl, one of these. Now this makes it 3-degree halide. Now, 2 types of reactions I just mentioned to you. One could be substitution reaction, the other could be elimination reaction. For substitution, it's be SN1. Now, substitution reaction will be favored in acidic solution, in acid. So, substitution reaction will be favored, that would be SN1 product. On the other hand, if I use strong base, what base is going to do? Pick up hydrogen from alkyl group. Let's change one of these R to CH3 so that you can see what's really happening. It says CH3. A strong base is going to pick up one of these hydrogens, become H2O, this make a double bond, and X leaves. So it gives you elimination reaction. Okay, so you're going to expect elimination reaction, and in this particular case, and this is going to be E2 reaction. When there is a strong base attached to it, and this is going to be for, if it's for 2 degree, I'm sorry, this is for 3 degree, it's going to be E1 elimination, and if it's 2 degree, let's make it 2 degree, with a strong base, is going to be E2. If I have this, it goes through carbocation, and then it would be E1. If it is elimination, elimination would be E1. If I have 2 degree, let's make it 2 degree, C, R, and let's make it CH3, X, and there is a hydrogen here, that's 2 degree. If I have a strong base, it would be E2. Remember, I said 1 degree, 2 degree, that would give you elimination reaction be E2, for 3 degree be E1, because it goes through carbocation, because this leaves, and then you get a carbocation. Next, I'm going to show you what we call Zaitsev rule that tells us which of the elimination product is going to be predominant. So Zaitsev rule is applied to determine the most dominant product of elimination. So I'm going to pick one of the homework problems from the book. That's chapter 7, number 16. And I'm going to show you the original question first. CH3, CH2, CHBr. This is a condensed formula, by the way. It doesn't explicitly show those bonds. CH3, CH3. So, what we'd have here is we'd have a base, a strong base, that's going to pick up hydrogen from adjacent carbon, carbon adjacent to this halogen, and then it's going to make a double bond. So, let's make elimination reaction, and we're going to write down 2 products, and we'll find out which one is going to be dominant. Now, let me show you which are the 2 products. Let's write down more explicitly these bonds. hydrogen goes in here, hydrogen goes in here, so there's a single bond here. This is the leaving group, so this is going to leave, no doubt. And in case of elimination, if your condition is such that it promotes elimination for a strong base, so for promoting it, you need to use a strong base. So it's going to be gone. So we're going to promote elimination reaction. Hydrogen can go from this side or from this side. So we are going to get two different products. And let's see what kind of products we get. If hydrogen goes from this side, this is what we end up with. C, it's double bond, C, because this hydrogen will be gone in the first case and makes a double bond here, Br goes. So you'd have CH3, CH2, CH3, and obviously you have the hydrogen. This is now sp2 hybridization, so that's angle going to be 120 degrees. And now you have, I think I mistakenly left out that methyl group. So that's going to be CH3 here and CH3 here. So that's one of the products. The second product would be removing hydrogen from this carbon. That's going to be CH3, CH, and then double bond, C, and then you would have C, CH3, CH3. Let's make sure that I have the same number of carbon. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yeah, I have the right number of carbons. So in one case, you remove hydrogen from here, make a double bond here. That's this case. Or remove it from here. So that's C, CH3, CH, double bond C, then this C, and then 2 CH3. Now, in Zeit-step rule, we find out, focus on what is being bonded to the carbon-carbon double bond, other than hydrogen. And those are called branching, or branch points, or substitution groups attached to the double bond, other than hydrogen. This is one of them, second of them, third of them. So there are 3 branch points, or 3 substitution groups attached to the double bond. Remember, you ignore hydrogen. In this case, also you can see here, this is going to be 1, and keep in mind there is 1 hydrogen in here. That whole thing makes 1 substitution group, second substitution group. So there are 2 branch points or 2 substitution groups. So which one is going to be dominant? This is going to be the major product. So Zeit-step rule tells us that when there is more than 1 alkene products, the products with larger number of substitution groups attached to the double bond would be more dominant. So accordingly, this is going to be more dominant. Make sure you try other problems, and that will give you a good understanding. And there will be 3-4 questions on naming. So make sure you go over the naming carefully. And also naming may involve R and S. So I'll give you a compound where there's an R and S possibility. In those cases, we'll write down the structure like this with thick lines. This is towards you. This is on the plane. So I'll give you OH. Say this is H. And there's another group in here, so Cl, Br. If I give you something like this and ask you to name this compound, in addition to writing down the name, you have to assign R or S and go by the rule. Remember the highest priority group, hold on to that. Go to the second highest, go to the third highest. If you're taking a right turn, that's R. If you're turning left turn, that's S. Now, this concludes my review for exam 4.